In this video, we are going to look at some applications of Gauss's law. Remember, we want to find the electric field in space due to a point charge or some collection of charges. Gauss's law makes that easy given certain geometries. First, let's remember the definition of Gauss's law. Gauss's law states that the flux of an electric field through an area is equal to the charge enclosed over epsilon sub 0. Now consider we have a charge Q, and we want to find the electric field due to that charge around that charge. So to use Gauss's law, let's first draw a sphere around Q. So on the sphere, the normal vector points radially outward from Q along the radius. Well, E also points out along the radius. So it's write Gauss's law, integral of E dot dA equals Q over epsilon sub 0. Well, in this case, E is parallel to N everywhere. So E dot N is just the magnitude of E times N, the magnitude of N, which is 1. So the magnitude of E times the integral of dA, well, the integral over this entire surface of dA is just the area of the sphere. So this equals E times the area, which equals E times 4 pi times the radius squared. Well, then this equals above Q over epsilon sub 0. Now, if we solve for E, we get 1 over 4 pi epsilon 0 times Q over r squared. And since we know E points radially outward, then we can make E a vector by adding on the r vector. Now consider we have a line charge with charge density lambda. And we want to find the electric field due to this line. So the next Gaussian shape is a cylinder. So let's draw our cylinder and say it has radius r. So the electric field due to the line points radially outward along this part and is perpendicular along the ends of the cylinder. So it's 0 on the ends. Next, the charge enclosed equals our charge density times the length of our wire, lambda L. So now, write down Gauss's law, the integral of E dot dA. Remember, E is parallel to the normal vector within the cylinder. So this is just the magnitude of E times the surface integral of dA, which is just E times the area, which in this case is E 2 pi r times L. So E times 2 pi r L equals our charged enclosed over epsilon sub 0, which is lambda L over epsilon sub 0. The L's cancel out, and so E is 1 over 2 pi epsilon 0 times lambda over r hat.